So we have just covered half of the chapter of ray optics. Now after this we are into the topic called refraction through the spherical surfaces. Now refraction through the spherical surfaces deals with few of the points, that is, I am relating the parameters associated with the medium, two mediums to be precise, mu1 and mu2, describing the refractive indices of the two medium, and also where is the object and where will be the image formed. So I am relating these two parameters across the spherical surfaces. So let's find out how to do it. Now we will learn about refraction from the spherical surfaces. Right now, the different topics which we have covered as far as refraction is concerned, it deals with the refraction across a straight surface or a plane surface, whether it's a glass slab or a surface of water separating air and water. So we have been dealing with plane surfaces for a while now. So right now we will look into the refraction from the spherical surface and why is it of such a good importance to us. The reason why it is very important to us, because the different things which we look around is through our eyes, and an eye is basically a refracting surface of spherical surface, or it has a spherical nature to its surface. So it becomes quite a lot of let's say of value to study the refraction through spherical surfaces. So let's get started. Now, spherical refracting surfaces, so first we will get on with that is how to make them and what they look like actually. So a refracting surface which is concave towards the rarer medium is called as concave refracting surface. So that's how they are being defined. A refracting surface which is kind of concave towards the rarer medium. Mind it, rarer medium or a denser medium has to be of reference. If it's concave to rarer medium, so that's why we have put it concave to rarer medium, concave refracting surface. Convex to rarer medium, convex refracting surface. A refracting surface, obviously, convex to the rarer medium will be known as convex refracting surface. Now, I'm just specifying it out, that is rarer medium, denser medium, and what is concave and what is concave. So obviously it makes sense. The first one is being the concave refracting surface, the other one is convex refracting surface. Now, the sign convention which we usually follow in this particular interaction or the phenomena of light is same as what we have been following for the reflection of light. That is, the direction of the propagation of light is considered to be the positive. Distance is measured from the pole of the refracting surface in this particular case, not the reflecting surface, and the positive quantity are those which are above principal axis, and those having a negative value are those which are below the principal axis. So the incident ray is taken from left to right, or basically the direction of positive quantities. All the distances are measured from the pole of the refracting surface, as mentioned earlier, same as that of reflection. The distance measured along the direction of the incident rays are taken at positive, and against the direction of incident ray they are taken to be negative. The vertical distance measured from the principal axis in upwards direction they are positive, in downwards direction they are negative. That's how the things will pan out, and I've been telling it repetitively that the sign convention which we follow for reflection is exactly the same what we follow for refraction. So please keep that in mind. That is, nothing new has been introduced other than the phenomena of refraction. That's it. So now let's warm up ourselves regarding the refraction at different spherical surfaces. How exactly will it look like in front of me? So we will start off with refraction at convex surface, that is from rarer medium to denser medium, and the convex is towards the rarer medium. So as convex is basically is convex to the rarer medium, so it's convex refracting surface, and I end up getting a real image because it moves towards the normal. Right? So an object is over here, the light ray gets in, moves towards the normal, so I end up getting the image at this particular point. So that's a real image. That is, there is an actual intersection of light rays at this particular point. So for me, the object kind of appears like this. That is, it literally becomes the source of the light for me. That the object is over here. Now these are the other credentials: normal and the point of incidence, angle of incidence, refraction, alpha, that is the incident ray, the angle which the incident ray makes with the horizontal or the principal axis. Beta and gamma, they are of angle of particular importance. Why? Because they will be helping us in relating angle of incidence, a refractive index, alpha and refracted angle, incident angle. All these aspects will be related, and for that I need gamma, beta and alpha, those quantities which will help me establish a connection. So this is radius of curvature, u and v. So the u, object distance, v, image distance, r, radius of curvature, a parameter belonging solely to the surface. So these are my quantities. Angle of incidence, angle of refraction, these are the other quantities. So what we are doing is, the genesis of alpha, beta and gamma is so as to relate these parameters: object distance, image distance and the radius of curvature, which is the parameter, the sole parameter describing the refracting surface. So as I have told you the agenda, now we will simply work it out using triangles. I is equal to alpha plus gamma, gamma is equal to r plus beta, or r is equal to gamma minus beta. Then with the help of simple triangle, picking up triangles, I can define tan alpha, I can define alpha to be exactly this. Why? Because I have considered the angles in these scenario to be pretty small, so that I can end up dropping tan or sine whenever I want to keep it simple. So again, tan beta will check out to be beta is equal to ma by mi. Just looking at the triangle, it's a simple trigonometric ratio, so you don't need to be worried about it. So what you can do is, if you are still feeling sort of, butterflies in the stomach regarding this concept, just try to work along what's being written over there, and then you will figure out why were they introduced in the first place. The agenda being relating u, v, r, angle of incidence, angle of refraction, the parameters describing refraction. Okay, so tan gamma will be ma by mc, or gamma checks out to be ma by mc. Moving on, Snell's law, again we will use the same concept over here, that is 1 mu 2 or 2 mu 1, depending upon where the light is entering and where the light is exiting. In this case, it's only entering, so sin I by sin r is basically mu 2 by mu 1, and I have two surfaces over there with different refractive indices, or I by r is equal to mu 2 by mu 1. Remember, small angle approximation is still in play, so that's why we are continuously converting sine and tan directly to their respective angles. Or mu 1 I is equal to mu 2 r. Again, we will be using this relation. Now I have a relation which relates angle of incidence and angle of refraction. So as I said, I, r, alpha, beta and gamma, right? We're replacing m by p. Now m by p is an approximation. M is a point where, or let's say the point m comes into existence where, when I actually draw perpendicular from the point of incidence A in the previous figure, if you will see, from A I draw perpendicular on the principal axis from the point of incidence. The point where it actually falls on the principal axis, that's m. So what I'm telling you is, basically, if this is the refracting surface, this is the angle of point of incidence. So if I draw a perpendicular, I end up getting this as m, and this is pole of the refracting surface. Over this, we are considering replacing m by p, because m and p, they are actually very close, and if I want to make sure that the angles with which I am playing with, alpha, beta, gamma, angle of incidence and angle of refraction, to be small, I need to make sure that it will actually happen when m and p will almost coincide with each other. So hence I am replacing m by p over here. So mu 1 by p naught is plus mu 2 by p1, pi is equal to mu 2 by mu 1 by pc. Applying sign convention with the values P0 minus U plus P1 Pi is equal to plus V, Pc equals to plus R, we end up getting this expression. So I'm sorry about the expression written over here, so make sure you do understand what's been written over here. That is, it's mu1 by P0. Over here it's mu1 by minus U plus mu2 by V equals to mu2 minus mu1 by R. That is the refraction to the convex surface. So please keep in mind, mu1 represents the medium in which the light is traveling initially. Mu2 is the medium in which the light will be traveling initially, where the image will be formed or the refracted ray will travel. And R obviously is the radius of curvature of that convex refracting surface. U and V, I guess I have told you that this is the object distance, this is the image distance. So each parameter which is very intrinsic to the setup, they are related beautifully over here. Refractive index and the distances of the object image. Now from rarer medium to a denser medium, that is, we will end up getting a virtual image. How? We'll figure this out. That is, if the object is actually very close to the refracting surface, so this is what happens. We end up getting a virtual image. Even in that, I will end up getting the same expression. If you have a close look at it, we still end up getting the same expression. So it's irrespective of what we do, we just need to make sure that we have to follow this equation irrespective of what's the refracting surface, what's the radius of curvature, whatever be the image or the object distance. It works out every time. Similarly, for convex surface, that is, now it's the other way around. That is from denser medium to rarer medium. And this is what happens, right? I've kept out the object in the denser medium and the light will move out in the rarer medium. So what we need to do is, now this mu2 and mu1, they are exchanging the roles. So the expressions will be completely swiped. The mu1 and mu2 will be exchanged completely. That is, in place of mu1, I have now mu2. In place of mu2, I now have mu1. And if you look at this, it's completely swapped right now. So what we can do is mu I minus U plus mu R by V equals to mu R minus mu I by R. That is, mu I and mu R basically stands for refractive index in which the light is actually traveling initially, and mu R corresponds to the refractive index in which the light will be refracted finally. So this is how we can actually put up with the general expression. Now for the concave surface from rarer medium to the denser medium, again with the concave surface yields a virtual image. So this is how this will be the picture. So again, as I've told you earlier, the expression will be same. So what you can do as a matter of practice is work this setup out. That is, the same triangles which we considered early on in arriving those expression, you can basically try it out for this particular setup as well. So again, it's mu1 minus U plus mu2 by V gives you mu2 minus mu1 by R. Now let's compare stuff of whatever things which we have studied for refracting through spherical surfaces. Refraction at convex surface from denser medium to rarer medium will give me, and in the end will end up, let's say, having a virtual image. Again, this particular expression mu2 divided by minus U plus mu1 by V is equal to mu2 minus mu1 by R. Refraction at concave surfaces end up getting virtual image. Expression corresponding to this will be again the same one. Keeping in mind that mu1 and mu2, the roles are swapped. So what you need to keep in mind is always this will come in handy. So why we are actually, let's say, compartmentalizing it for different cases and different distances is they will be very handy when you come across problems in competitive exams. You need to be very quick about it. So until and unless you are thorough with these expressions, you will be, let's say, 10 seconds behind the students who actually know about this. So as a student, I shouldn't be cramming up stuff, but obviously I need to come up with methods through which I can improve my efficiency. So in a nutshell, I basically want you to get hold of this expression. I don't want to get hold of all the 4 expressions, learn it by heart. I just want to make sure you understand what this setup stands for. And if I change the parameter, that is concave to convex, object placed near, far away, virtual image, real image, you are able to figure out in which place which value should be substituted. mu1, mu2, where does they actually stand? What's the meaning of that? So that's why I have written down specific scenario in which it's used. So if you're comfortable with one expression and able to figure out the rest 3 or 4 or 5 of it, that's the best case scenario. So I encourage you to do that. If you aren't able to do it, get on with this. Get on with these 3 or 4 expressions. Now, expression for object in rarer medium is same for whether it is virtual or real or convex or concave surface. So that's the case. So it will be the same, mu1 or whatever, irrespective of what type of image, what type of surface, I'll still end up getting this. The only thing which might change down the line will be switching of the roles of mu1 and mu2. That is, right now I have simply changed, put it on a flip side, that is, I have put the object in mu2 rather than mu1. So expression for object in denser medium is same for whether it's a real virtual image or convex or concave surface. As I've told you, simply role reversal of the case. mu1 becomes mu2, mu2 becomes mu1. Now the final set of comparisons. However, the values of u, v and r etc. must be taken with proper sign convention with while solving numerical problems. I think so it's just a reminder to make sure that every time you handle a particular problem, irrespective of what the topic is, reflection, refraction, dispersion, diffraction, you need to make sure the sign conventions are properly respected, because if I end up writing u to be minus 70, this makes complete different sense than u is equal to 70. Like completely opposite sense. So I need to make sure which one I am writing at which context. In the refractive indices, mu1 and mu2 get interchanged in the expressions quite oftenly. So that's the part which we have discussed extensively. So please keep this in mind as well. That is, I just pointed out the fact that they are exchanged, but you should keep in mind when are they actually exchanged and how are they actually exchanged. Let's try out a problem based on the refracting from the spherical surface. Let's consider a refracting surface like this. My intention is basically to find out the radius of curvature, r. The information which I have is I have placed an object at point A, and I observe that point A is at distance 20 centimeter from the pole of the refracting surface. I end up getting the image at the same point as on point A. That is, the object and the image were both at point A. So, and it's given that mu1 is equal to 1.5 and mu2 is equal to 2. I need to find out the radius of curvature. What is the radius of curvature when the object and the image are at the same point? So, mu1, so I will use this expression mu1 by minus u plus mu2 by v is equal to mu2 minus mu1 by r. Mu1, so I have the value of mu1, that is, I will substitute it over here. U is, minus u is plus 20, because u I will take it to be minus 20, so it becomes plus 20, minus mu2, v is minus 20. So it's plus mu2 divided by minus 20. And then I have mu2 minus mu1 by r. Now I will introduce the values of mu1 and mu2 over here. So mu1 is 1.5, mu2 is 2 divided by 20. Mu2 is 2 and mu1 is 1.5. I end up getting 0.5 r. Again, I can write r is equal to 20 divided by 0.5 multiplied by 0.5. I end up getting the radius of curvature to be 20 centimeter. That is the value of the radius of curvature. Now obviously I missed out the negative sign, so please introduce the negative sign over here because of the fact that 1.5 minus 2 is equal to minus 0.5. So introduce the value of A over here, so we end up getting radius of curvature to be minus 20 centimeter. Now we have just described few of the most important facts about refraction through spherical surfaces, which will be, please keep this in mind, will be of utmost importance while dealing with lens, which is an upcoming video. So let me just note down what are the different things which we have discussed. We have discussed what is a concave surface and what is a convex surface as far as refraction is concerned. That is, these two surfaces are decided by a denser medium and a rarer medium on the other side of the surface. And also, when will be the real image formed? When will be the virtual image formed? So these parameters corresponding to these setups, I do have mathematical expressions. So it's an utmost request to you, that is, please get hold of these expressions because it's very valuable and it will be used extensively in the upcoming videos and the problems which you might face in competitive exams.